Let's go through the mechanism to reduce an aldehyde or ketone using specifically lithium aluminum hydride. So we'll go through the mechanism first, and then we'll write the general reaction scheme. So let's start with a general aldehyde or ketone. We have lithium and the aluminum hydride anion. The lithium being present in solution with a positive charge, that's an open shell, lithium lost an electron. The lithium coordinates, this is not really a formal bond, but it's a coordination between oxygen and lithium. So this lithium is acting like a Lewis acid. So it acts like a Lewis acid catalyst by coordinating to the carbonyl oxygen. This increases the reactivity of the carbonyl carbon now. So coordinating the carbonyl oxygen and the lithium cation, this indicates that there are some electrons being shared, coordinated between the oxygen and the lithium. That is then reducing electron density around oxygen, which further reduces electron density around the carbonyl carbon, making that carbonyl carbon more electrophilic. Then we have our aluminum hydride. There are 4 hydrogens total. We will emphasize that one bond to one of the hydrogens to show that that is what is then being added. So the hydrogen with the electrons in the bond, we show that by the arrow starting at the bond. Those electrons will donate to the carbonyl carbon, and the electrons in the pi bond are then owned by the oxygen. So the product of this step, we've broken the pi bond, we still have the carbonyl carbon bonded to 2 R groups, and now this oxygen has a negative charge because it gained ownership over electrons in the pi bond, and we have a new bond to the hydrogen from aluminum hydride. Negatively charged oxygen is balanced by that lithium. Charge is balanced by that lithium. Now we have an oxygen with extra electrons, and we still have that aluminum hydride with only 3 hydrogens here, so we have an open shell aluminum. The carbonyl oxygen, this negatively charged oxygen, will bond to the aluminum. This forms another intermediate, still tetrahedral as it is in the past step. Now this oxygen has a bond to the aluminum. Aluminum's now negatively charged, and we still have that bond from the carbonyl carbon to the hydrogen. We have the charge balanced by the lithium cation. And now we again have a negatively charged aluminum with hydrogen atoms bonded to it. These hydrogen atoms can act as hydrides to reduce further aldehydes or ketones present in solution. So these hydrides are active in further reductions and because of this, each lithium aluminum hydride molecule can reduce a total of 4 aldehydes or ketones because there are 4 hydrogens available in lithium aluminum hydride. So 1 mole of lithium aluminum hydride can reduce 4 moles of the aldehyde or ketone. So we formed this complex here where the oxygen is bonded to aluminum. The aluminum with the 3 remaining hydrides will continue to react. And when that reduction is complete, we have aluminum bonded to 3 oxygens with the remaining carbon chain. So we have an aluminum alkoxide compound, and that is separated into what our final product would be in a separate step. So when the reduction is complete, the aluminum alkoxide addition compound ends up being protonated, and we do this in a separate step. So once the aluminum hydride has reduced 4 moles of the aldehyde or ketone, we then have this alkoxide bonded to aluminum. So we have an aluminum bonded to the oxygen, just like in the structure in the top right. Oxygen's bonded to carbon, 2 R groups, and that carbon's bonded to a hydrogen that was gained in that first step. The aluminum is bonded to 4 of these. Just like the aluminum can be bonded to 4 hydrogens, instead of being bonded to 4 hydrogens, it's bonded to 4 alkoxide groups. Now the oxygen needs to be protonated by some acid present in solution. So if we have an acid present, we'll represent as H3O plus. The bond between oxygen and aluminum will form a bond to the acidic hydrogen. We form water, and this will happen for all 4 of the substituents on aluminum. So for every 1 lithium aluminum hydride, we form 4 new alcohol products. We have lithium, and then we also form aluminum salts. The main product that we're worried about and concerned about in this reaction is this alcohol. So remember, if we have an aldehyde or ketone, we use reducing agents, we form an alcohol product. So the general scheme for this reaction just to summarize what we did in that mechanism, we start with an aldehyde or ketone. We add lithium aluminum hydride with an aprotic solvent. Now we said this is usually an ether. In a second step, we add water with some acid. So the lithium aluminum hydride, remember we said that reacts violently with water. So we can't have lithium aluminum hydride in the presence of water. The water must be added in a second step. So we have H2O and some acid. Now the acid can be like HCl, HBr, any strong acid that will protonate water molecules. Should be added to the water solution. We must do this in 2 steps. And then in the end, we form an alcohol product. So the carbon is still bonded to 2 R groups. The oxygen, the carbonyl oxygen, is an alcohol, and a hydride was added to that carbonyl carbon. So this is the reduction with lithium aluminum hydride.